Hello, my name is Luis, and I'm an undergraduate student at the National Institute of Telecommunications, and my work is called Evaluation DETR, RetinaNet, and RTMDet models for object detection in rural drone imagery. The co-authors are Rafaela, Felipe, Samuel, and Usualis. So, talking about the transformative power of AI, artificial intelligence has been transforming various sectors with applications ranging from medical diagnostics and advanced security systems to deforestation monitoring through satellite imagery and autonomous vehicle operation. These innovations have significantly enhanced efficiency and precision, reshaping the way complex problems are addressed. AI driving innovation in agriculture. The agricultural sector in particular has greatly benefited from AI advancements. Applications such as pest detection, harvest optimization, detailed soil analysis, and monitoring of hero elements like crops, animals, and agricultural machinery demonstrate how technology can drive productivity and sustainability in farming. This study focuses on exploring and comparing different object detection models with distinct characteristics, RTMDet, DETR, and RetinaNet. Each model offers unique advantages, providing tailored approaches to address the challenge of object detection in rural aerial imagery. Our primary objective is to evaluate the performance of these models and assess their suitability for high-precision agricultural applications, contributing to the development of cutting-edge technological solutions in the sector. So here we have some related works. And in the first study, detection and classification of objects present in aerial drone images of urban environments, the research targeted four main object classes: people, small vehicles, medium vehicles, and large vehicles. The YOLO V5 model was employed, known for its efficiency in real-time object detection tasks. This study highlights the application of AI to enhance urban monitoring, offering insights into the model's ability to handle heterogeneous objects in densely populated areas. In the second study, Smart Agriculture via Object Detection, the authors explored the use of convolutional neural networks for classifying plants and pests in an agricultural context. The research involved the classification of 40 different classes, covering a broad diversity of agriculture-related objects. However, the authors identify a significant limitation. All training images were collected from a single geographical region. This restriction could hinder the model's ability to generalize to objects from other regions or time periods. As a solution, the study recommended incorporating images from diverse locations and seasons to improve the model's robustness and generalization capabilities. In contrast to the aforementioned studies, the present work takes a different approach. It focuses on using aerial images captured by drones in rural environments, with the primary aim of comparing the performance of various object detection models. The methodology used in this study follows four main steps: dataset collection and preparation, model selection, fine-tuning of model weights, and performance evaluation metrics. We will begin by discussing the first step, dataset collection and preparation. The first step is image collection. The initial step involves collecting images within the desired context. For this study, images were obtained using drones in rural areas, supplemented by publicly available images. Class definition. The detection classes defined include soybean, cornfield, coffee plantation, forest, pasture, car, and house. Analyze object by classes. The dataset was analyzed to ensure a similar number of samples for each class to promote balanced training. Object annotation. Each object in the images was annotated using bounding boxes. This task was performed using RoboFlow platform, which generates annotation files compatible with training and validation processes. Image preprocessing. Images were resized to the input dimensions required by the model, 640 by 640 pixels, and black padding was added to unused areas to avoid distortion. Data augmentation. To increase dataset variability, techniques such as horizontal and vertical flipping and noise addition were applied. Dataset splitting. Finally, the dataset was divided into 945 images for training, 93 for validation, and 93 for testing, totaling 1,131 images. The HoboFlow platform was used to dataset exportation in the COCO detection format, which is compatible with the detection framework used in this study. The selection of models was based on two main criteria: frame rate per second and accuracy on large datasets. The three models chosen for this study were selected due to their strong performance metrics and availability within the detection library. For DETR and RetinaNet, the chosen backbone was ResNet 50, while for RTMDet, the large version was selected. Those configurations were chosen for the high accuracy and reasonable frame rate per second, making them suitable for this study's objectives. More models were tested, however, the table below only shows the key parameters used for selecting the models. Here we have the chosen models. RTMDet is a model designed to outperform the YOLO series by combining efficient convolutional neural networks techniques with advanced optimization strategies. It is highly versatile and can be used for various object detection tasks. RetinaNet was developed during a time when two-stage detection models were the standard. To optimize this process, RetinaNet adopts a one-stage detection approach, making a single pass through the image and simplifying the network architecture. This model excels in detecting objects across multiple scales, effectively distinguishing background elements from foreground objects, resulting in robust detections. DETR leverages transform techniques, eliminating the need for some pre-processing steps. This allows DETR to simplify object detection while achieving performance levels competitive with other detection models. Now, talking about the fine-tuning process, all models were pre-trained using the COCO database. Therefore, it was necessary to fine-tune the network weights for the specific task of object detection in rural context using aerial images. For the fine-tuning process, the collected database was employed. For training the DETR model, the layers were frozen. For training the RetinaNet and RTMDet models, the layers were not frozen. A small initial learning rate was used, which decayed progressively throughout the training process. The mini-batch size was set to 16 images. These parameters were selected after conducting multiple experiments, and they provided the best results for this study. The performance evaluation metrics used were recall. Recall measures how many objects of the desired class present in the labeled images were correctly detected. This metric is calculated using the formula shown to the right, where TP represents true positives and FN represents false negatives. Precision. Precision evaluates the accuracy of the model's predictions, indicating how many of the detected objects actually belong to the correct class. This metric is computed using the formula shown to the right, where FP represents false positives. Mean average precision, or MAP. The MAP is calculated by averaging the average precision values for each class. AP is derived from the area under the precision recall curve, providing a comprehensive evaluation of model performance. The loss function measures the error between predictions and labels, serving as a critical component of the model training process. It guides the adjustment of the model's parameters, enabling it to improve its performance over time. Right below is a table presenting the results obtained in this study. As we can see, RTMDet achieved the highest MAP, but it had the lowest FPS. DETR recorded the lowest MAP and a median FPS, and RetinaNet demonstrated a median MAP, the lowest loss, and the highest FPS. These results highlight the trade-offs between accuracy and performance across the models. Here we have the confusion matrix of RetinaNet, and it shows us notable challenges with the classes coffee, house, and pasture. Unlike RetinaNet, the confusion matrix of RTMDet highlights difficulties with the classes coffee, house, and soy. For DETR, the confusion matrix shows significant challenges with the classes coffee and house. Across all three models, the classes coffee and house exhibited lower than expected precision. This may be attributed to specific characteristics of these classes. The coffee typically grow in irregular terrain with varying topography, making it more complex to detect consistently. The house usually shows a high scale variance, which likely contribute to the lower precision. In conclusion, it's now possible to identify the best performing model. Although RTMDet achieved the best metrics overall, the DETR model, as we tested, proved to be the most effective in real-world scenarios, delivering accurate classifications with precise bounding boxes. For future work, several improvements can be explored. The first one, implementing models from scratch. Developing the models from scratch could enhance their performance, particularly in terms of FPS. The detection library supports a variety of models, and its pipeline might impact performance negatively due to its generalist approach. The second one is expanding the dataset. Increasing the dataset size could significantly improve results. Classes with high variation, such as house and coffee, require more samples to achieve better generalization. The third, onboard model inference. Executing model inference directly on the drone could save resource by eliminating the need for server-based image inference. So these steps could further enhance the model's performance in detecting objects with rural settings using aerial imagery. So some acknowledgements. This work was partially funded by Intelbras, ProEducar program, CNPq and FAPEMIG, and XG Mobile, Embrap, Inatel Competence Center on 5G and 6G networks, and the recognition to the collaborators from YLab, Inatel, and University of Brasilia. Thank you for the attention.